So hello everyone, today we'll be solving AtCoder next DP contest. The original AtCoder DP contest was quite a fantastic resource for dynamic programming. Most of us, including me, learned DP from there, solving those problems. And I'm expecting this one also to be great. Let's have a look at the first question. The first question is titled as polyomino. You have an unlimited number of the following types of polyominoes. A rectangular polyomino of size 2 cross 1. An L-shaped polynomial formed by removing one 1 cross 1 square from a 2 cross 2 square. Fine. You are given a grid of size 2 cross n. You want to completely tile all the cells of the grid using these polyominoes under the following conditions. Each cell of the grid must be covered by exactly one polyomino, so you should basically fill it. And you are allowed to rotate the polyominoes while placing them. Find the number of ways. Okay, you need to find the number of ways. First, let us take the input. Input is quite small. Input is quite small. Okay, we have this extension right. Wait, why isn't it working? Do I have another VS Code open somewhere? Let's close it. Okay, this thing is still loading. Let's wait for some time. Let's read the question again. Till then, let me explain it. Okay. So the question says you'll be given a 2 cross n grid. That means it would have 2 rows. Okay. Now I'm unable to draw a rectangle. So let's do it this way. Yeah, a 2 cross n grid. It would have n cells in each row. So now this is a 1, 2, 3, 4, 5, 6. It's a 2 cross 6 grid, right? And you're allowed to fill it in two ways. Either you can do a vertical domino, it's a domino, or a horizontal domino, or maybe you can do some sort of an L shape, and you're allowed to rotate. So if I rotate a vertical domino, it would become this, but a horizontal domino already exists, and if I rotate a horizontal domino, it would become the vertical domino, and vertical domino already exists. So it doesn't make sense doing it that way. And if I rotate it complete 180 degrees, horizontal would become horizontal once again, vertical would become vertical once again. So it doesn't make any sense rotating the vertical domino. Now coming to the rotating L-shaped domino. To understand rotation properly, how it works, let us take one side of L-shaped domino green, other side be red. So this is the initial configuration. Now if I rotate it, it would become this, right? And if I rotate it once more, this, and if I rotate it once more, it would become this. Okay, so somewhere you're getting mirror images. All that makes sense, all the configuration that makes sense is this one and this one, because you'll be filling from one side, right? If you're already filling this way, then this thing doesn't make any sense, isn't it? So mirror images are of no use to us. If you're doing this and this, it's a meaningful configuration. So you can't fill it from both ways. If you want to check, you'll understand the statement while maybe try running this code once again on a notebook. But yeah, mirror images don't make sense. This is fine, even this is not fine. So these kind of things we need to avoid. Some configurations would be pruned. We need to figure out which configurations they are. So let's check if its extension is working or not. Yeah, finally. I was recently studying about people's attention span, and I have decided I would not keep more than 2 problems in a single video. Contest streams are fine. I cannot do anything about it, but not more than 2 problems today. Okay, so Yeah, we need not take the grid, I guess. I don't think we can solve it using a grid. Let's see how can we solve it. So initially we have an empty grid. Always think, always when you start a DP problem, always do something known as a complete search. Start from a complete search. Okay, start from a complete search. Complete search is basically trying out all the possibilities. So initially you have an empty grid. Let's denote it with this node. You can either start from filling it with a vertical row, filling with a horizontal row, or filling it with a L-shape row. This L-shape or this L-shape would lead to the same kind of possibilities, right? Since they both are mirror images, isn't it? Isn't it? So L-shape, whatever the possibilities are there, you'll multiply them with 2 because they're 2 images. Yeah, either you can choose bottom L or you can choose this one, the flipped L. Okay. So we need to figure out when you're doing a complete search, you need to figure out that what is this configuration leading to, what is this configuration leading to, what is this configuration leading to. Fine. So when you have a grid like this, let's once again draw it. Okay, let's once again draw a 2 cross 6 grid. So 1, 2, 3, 4, 5, 6. When you're placing a vertical one, initially it's a 2 cross 6. Initially it's a 2 cross 6, isn't it? Initially it's a 2 cross 6. When you're placing a vertical one, what is this becoming? What state is it pushing to? It's pushing you to a state where you're having 2 cross 5 grid. So let there be a state called F. F means full. F means full. Let's call a state full. When you give full 2 cross 6, when you give 2 cross 6 to full and it places a vertical thing, it takes you to a configuration of full of 2 cross 5. Full of 2 cross 5. And this 2 is what do you say? Unnecessary data. We can eliminate it in both the states. So f of n can take you to f of n minus 1, isn't it? F of n can take you to f of n minus 1. And now let's talk about the second possibility. When you're placing a horizontal one, when you're placing a horizontal domino, since we are given that, I guess we are given unlimited moves, you can place any number. Unlimited number of the following two types of, yeah, you can place unlimited. So if you place 2 here, because I want to fill this, just because I want to fill this, why should I place only 1? I can place 2, right? So this is giving me a 2 cross 4 grid. That means f of n, f of 2 cross 6 can lead to f of 2 cross 6 can lead to f of 2 cross 4. Okay, that means f of n can lead to f of n minus 2, isn't it? F of n can lead to f of n minus 2. Call it equation 1, call this equation 2, just like school kids do. Okay, so now it's time to place L shape. Okay, when you place an L shape, this gets interesting because it's neither leading to a new grid, right? It's not a complete grid. There's a kind of gap here. Isn't it? There's a kind of gap here. So that means you cannot represent this configuration. You cannot represent this recurrence as a complete grid. That means you cannot represent it as a full grid. You cannot represent it with F. Therefore, we are taking a new state variable. We are taking a new thing to represent this. Okay, we are taking a new variable g. We are taking a new function g. G denotes this configuration basically. Like everything is there. There's a one extra capsule. These kind of shapes, or maybe these kind of shapes. These kind of shapes can be represented using a function g. So this is leading you to g of n. When you place g of n, that means here if you place a L shape, g of, if you place a 2 cross 6, it is leading you to g of n minus 1, which is g of 2 cross 5. It's leading you to g of 2 cross 5, isn't it? isn't it? It's leading you to g of 2 cross 5. Fine. It's leading you to g of 2 cross 5. That means g of n is leading you to g of n minus 1. You may be like, hey, this is g of n. This shape is called g of n. This shape is g of n. And it's leading you to this. It's leading you to this. How did this become g of n minus 1? How did this shape become g of n minus 1? Okay, a valid question, but I already justified that mirror images, these both are to be considered as same. These both are to be considered as same. Fine. Fine. And one more thing, actually, we missed something. We missed something. What is it? This f of n, on placing an L shape can lead to g of n minus 1. This f of n can lead to g of n minus 1. And when placing this L, it can lead to g of n minus 1. f of n on placing this particular L, if you place, let's say, this particular L, before it was this particular L, now if you place this particular L, f of n would lead you to g of n minus 1 once again, isn't it? This shape is called g of n minus 1, isn't it? So once again it would lead you to g of n minus 1. Once, let's see what all f of n is doing. F of n on placing a vertical is leading you to f of n minus 1. F of n on placing two horizontals, since we can place unlimited, it's not a big deal, it's leading you to f of n minus 2. F of n on placing L shape, this L shape is leading you to g of n minus 1. On placing this L shape, it's leading you to g of n minus 1. Since I'm counting the total number of ways, I should sum them up, isn't it? I should sum them up. If I sum them up, I get the recurrence relation for f of n, which is equal to f of n minus 1 plus f of n minus 2 plus 2 times g into n minus 1. Fine? 2 times g into n minus 1. 2 times g into n minus 1. I get this recurrence relation. Now, since we have started to compute for g also, we need to check what leads to g, or we can basically say we'll do the same thing for g also. So g of 2 cross 6 leads to g of 2 cross 5. That means g of n leads to g of n minus 1. If I place one L shape, it leads to some other L shape. It leads to g of n minus 1. When would this happen? This would happen when I place a extra horizontal with this. What do I mean? Let us understand. Let's say I've placed it this way. If I place a horizontal here, which state is it leading me to? Okay, which state is it leading me to? It is leading me to, if this was supposed to be g of n, this was supposed to be g of n, this was supposed to be g of n. Now I have this, which takes two columns. This was taking only one column, so this was g of n. This is taking two columns. This is g of n minus 1. Fine. This is g of n minus 1. Okay. When I place a horizontal, this happens. But what if I end this with this one? What is this state leading me to? An L and L forming some sort of a, joint kind of thing. It is leading me to. Before it was a 2 cross 6 grid. Now it was 2 cross 6 grid. Now it became a sorry, it was not a 2 cross 6 grid. One thing was already covered. Okay, so from this thing I have reached to this particular state. That means it's a 2 cross 5 grid. This thing is a 2 cross 5 grid. However, it has one extra thing here, extra block here, which is filled. It led me to a 2 cross 3 grid. That means g of n also leads to f of n minus 2, because full grids are denoted by f, right? So g of n equal to g of n minus 1 plus f of n minus 2. So finally, we have derived a couple of recurrence relations. Now it's time to code it up. First thing, what are the states which we are using? We are using f of n minus 2. To use this state, f of 2 must be defined. So we need f of 2. And here also we are using f of n minus 2. So it should be defined. Alright, it should be defined. Okay, that's it. So we need to define till f of 0 equal to, if it's nothing, we have one way. F of 1, if it's a 2 cross 1, we have one way. Okay, if it's a 2 cross 1, we have one way, right? If it's a 2 cross 1, it's a 2 cross 1. A vertical is enough. We're done. 0 and 1 are defined. From 2, we can start for int I equal to 2. Okay, as I said, we are calculating f of n minus 2. So f of 0, f of 1 are the prerequisites. DP requires it. DP requires those two previous states. So we have computed them. Now we need something else, which is G. Let's call them full and gap, because I'll be documenting this in a GitHub repo. So if someone wants to refer it later, it would be understandable if I keep descriptive variable names. So gap of I is equal to gap of I minus 1 plus full of I minus 2. Isn't this the recurrence relation for G? This would occur when you place an extra horizontal domino. This would occur when you make it a, there's a word for it, like we call something when it's some carpentry related word, jagged or something, right? When it's, I don't know it's the right word or not, it's basically like forming a joint, like it's forming this kind of thing. Okay, yeah, to else. Okay, this way, it's forming a joint. So that becomes a full I minus 2. Then we need to compute full of I. Full of I is equal to full of I minus 1 plus full of I minus 2 plus 2 into G of, or else gap of I minus 1. And our answer would be 8. We need to fully fill 2 cross n grid. So full of n would be the answer. Done. Let's try to run this. Compilation aborted by user. Yeah, accepted. So let's submit this. See, the basic idea is we need to do a complete search, and this is always whenever it's a counting related problem or some choice related problem, it should be a complete search. You can ask me, when is it not a complete search? When is it not a complete search? There would be cases when you're storing the results of some computation. Here also we are doing the same, but the intuition is different, you know. Okay, so this got accepted. We will be coming across problems where the mindset doesn't work. Maybe it would still be a recurrence relation. It would still be everything same, but it requires two different mindsets to solve some problems. You're given a simple directed graph with n vertices and m edges. The vertices are numbered from 1 to n. The ith edge goes from vertex ui to vertex vi. This graph has no cycles. The name DAG was pretty clear. Find the number of paths from vertex 1 to vertex n modulo this. You're given t-test cases, solve each of them. Fine. So let's take this first. Yeah, let's write a method void solve. Alright, so we need to find the number of paths. How can we do it? The mindset was doing a complete search in the previous problem. The mindset of that particular problem was doing the complete search. But in this problem, this shouldn't be the mindset. Here, the mindset, since we are traversing a graph, first thing we need a graph traversal. Maybe a BFS or maybe a DFS. You can do it either way. Okay, you can do it either way. Uh, Honestly, a BFS would be a better choice for this because it's more intuitive. Fine. And here the mindset is aggregating. Here the mindset is aggregating count. Okay, you might be like, how do you actually come up with these kind of mindsets? Like when solving some problems, you're saying it's a complete search problem. You're saying it's a complete search problem. Here you're saying it's aggregating related problem. So how do you actually do it? Like how to figure out, how to figure this out, how to go in the right direction. So the thing is that in the previous problem, we had configurations. We were dealing with configurations. So it's a total different form. Here you need to check all the possibilities. But when it comes to this one, you already know the possibilities. In the previous one also you knew the possibilities. Again, I'm telling you, if you think it in a complete search, you would still get an answer, but it won't be that intuitive. Here the mindset is when let's say traverse three nodes, I would aggregate their number of ways, like it's one way, two way, three way. Then when I visit the children, I would add this way, this way, this way. So how many ways is it? Okay, how many ways is this? Okay, how many ways is this? So here there's nothing. Three ways. Each of them have three. So this is what I'll be doing. I'm aggregating it, right? Like it's an accumulation of number of ways. So I'm basically summing up for each node. You can call it complete search because you are still visiting all the nodes, but don't you think this is more intuitive? This leads you to a direct solution. Just do a traversal, add the number of ways. So in the previous one, DP array was used to store number of ways. In this case, like you're not doing a complete search. DP array would store the number of ways till a particular node. See, there's a difference, right? Later you'll add those other node values. Okay. So let us understand this problem. All you need to do is a simple BFS. So first thing, sorry, directly we can't take into int. So let's take int n. Is it n itself? Int n, number of vertices and number of edges. So sorry there was a small power cut. We were discussing something. Yeah. So in the previous problem, it was about complete search. We had to explore all the possibilities here. In this problem, exploring these possibilities is the main thing. If you know f of n gives f of n minus 1, n minus 2, g of n minus 1, g of n minus 1, and g of n gives g of n minus 1, f of n minus 2, the problem is over. Okay, this problem was about complete search, which is building recurrence relationships this way. But here also you may argue that it's still a complete search, right? You're taking one node, you're picking one node, you're exploring all the possibilities from there. So yes, it is complete search. Indeed, it's complete search. But does that solve the problem? Say you know this part, that what all you need to explore, you know it. Is it solving anything? It's of no use, right? You already know graph has children and you need to visit the children. So complete search, it is complete search, but just by knowing it's a complete search and implementing it doesn't solve the problem. Here we need something known as aggregation. Okay, the mindset required to solve this is aggregation, which is you need to take every node, calculate its children possibilities, and then you need to count them basically. So wait, let me minimize it. Yeah, fine. So before that power cut thing, we were taking edges. So int u, b, c in u, and b. Now we need to make a vector int adj adjacency list. For n+1 nodes. Fine. Alright, so we'll be doing adj of u dot. Let's make a hash define here. Adj of u dot pushback v. Now let's use the BFS to explore all the possibilities. Like, to do the complete search, figuring out it's a complete search is not a big thing here because it's very simple thing, right? Alright, so we need a q, int q. Okay, we'll write a simple BFS node equal to q dot front, q dot pop, and neighbor in adjacency list of node. What happened? Yeah, okay, fine. Okay, we need to do here maintaining a visited is not a good idea. Here maintaining a visited is not a good idea. Instead of visited, can we maintain some other data structure which would take the in degree? Why am I saying this is, see, if you're currently at a node, you need to find out the number of paths from vertex 1 to n. So if you're at a node, okay, if it's a start node, that means in degree of this node is 0. There's nothing coming inwards towards this node. Everything is outgoing from this. This is a perfect node to start with. So if I take a vector int in degree of size n+1, initially in degree of every node is 0, and when I do this pushback, I'll do in degree, since okay, u is pointing to v, in degree of v would be incremented. If after all this also you find somewhere, if you find that okay, I'm coding pretty slow compared to my actual thing. If you find that in degree of something, if in degree of some I is 0, you will make it as the start node. That means you will push it into the queue. That means queue should be here. Fine. Okay, in degree is 0, that means you need to start visiting from here. And once you're iterating over neighbors, you need to maintain, since we are aggregating stuff, vector in dp. Okay, vector in dp of size n+1, we need to calculate for n+1 vertices. dp of first vertex is 1. If you have reached vertex 1, that means you found one valid path. You can say it that way if you're coming in reverse. But if there's only one node, there's only one path. Like if it's a singleton graph, like there's only one node. That means there's only one path. 1 to n is just one path. You can take it that way, or else think recursively. How would you think recursively? Let's say this is some node, this is the nth node. From here, this is a path, right? If you have reached to the first node, that means you have found one way. You can either take it this way. So basically dp of 1 is 1. And when you are iterating over neighbors, all you need to do is dp of neighbor equal to dp of node, dp of parent plus dp of neighbor. Fine. dp of node equal to dp of node plus dp of neighbor, and we are supposed to do a modulo here. We haven't taken that modulo yet, so let's quickly take that modulo. Where is it? Yeah, done. After doing this, you have visited that one path, right? You need to remove it. That means if I'm at this node, if I have, okay, initially what you're doing is in degree of this node is 0, so you're visiting its children. Let's say in degree of this node, okay, in degree of this node is also 0. That means you should remove, you should remove this path. You shouldn't consider this path. Accept this path, consider the remaining. If it's this way, now in degree of this thing is 0 because you're not considering this. It's a separate instance. Okay, this whole thing is an instance. This is a separate instance. Can you feel the recursion here? What's happening here? So you need to eliminate this path. That means before actually doing this computation, when you're doing this computation, sorry, not here, wait, in degree, you need to make this in degree as in degree of neighbor minus minus, so that you remove its connection with the parent. Now if in degree is 0, if in degree of neighbor is 0, okay, it could potentially lead to a new path. So what's the use of it? What exactly are we doing? When you're doing this, you're pruning this path. So that double counting doesn't happen. Okay, this is what you're ensuring, that double counting doesn't happen. You're pruning that path. Okay, you need to do q.push neighbor. Done. And final answer, where would the final answer be stored? You need to reach, okay, dp of some x denotes, in this case, number of ways to reach x. So number of ways to reach n would be dp of n. Done. So let us submit this. So now I'm thinking, how would I edit that PowerPoint video? It's extra burden for me now. Okay, I hope the two problems were clear. Most importantly, this mindset of aggregating stuff and doing the complete search this way is clear. In this problem, the complete search doesn't play any role, so it's more of this aggregating logic in DP. Yeah, so I'll be creating a whole playlist of this, so stay tuned for this. Hopefully we'll be having a good practice over DP. And remember one more thing, if you're trying this on your own, and you're not getting it properly, so let me tell you, the problems aren't that easy. It's not that easy as the original AtCoder educational DP contest. Okay, the problems are a little bit ahead of your level. It could possibly be. If you're a complete beginner, I would suggest educational DP contest is a better resource for you. But even these problems are good. If you're trying to practice forms, you're learning intermediate DP, you want to solve some lead code force kind of thing, then I feel these are the questions. Yeah, this could be asked in lead code 3 or 4 in lead code contest. It's somewhere at that level. So thank you everyone. I'll have to edit the video.